Welcome to this course on fundamental concepts of electricity supply systems. In this course, we shall consider certain basic concepts in electricity supply systems and try to build up from the basics to the operation and control of a power grid. Now, this course assumes that you have had some basic courses done already by you in electromagnetism, basic circuits, basic mathematics. Some of the concepts which you will be discussing in this course will be familiar to you already. In fact, what we will be doing in this course mainly would not be deriving or deriving in a mathematical sense all concepts which you have learned in electrical engineering or in high school physics, but concentrate on a few important concepts. In fact, we have an exciting set of experiments and illustrative examples lined up for you. The first part of this course will cover low frequency electromagnetism and its relationship to basic circuit theory. In fact, we shall consider even certain circuit components and their non-idealities. When we look at electrical supply systems, we need to look at it from a very fundamental perspective: why AC, why DC, why three phase, why what is the neutral, why is it grounded, what are the safety issues, and we shall also therefore understand some important practical aspects of the engineering of electrical supply systems. Once we understand the basic concepts of circuits and electromagnetism, we will be able to go forward and try to build up a simple local electrical supply system in which you have got a generator supplying a load, and some of the important aspects relating to it, which include the control of frequency in an AC system and voltage in an isolated system, will be covered. In fact, one of the important changes which is occurring in or rather we can say that has already occurred, is that most of our electrical loads, many of our electrical loads are now being supplied through some power electronic interface. We shall see later that even in the case of electrical generation through wind and solar, many of these generators are actually mediated through power electronic interfaces. So, power electronics is an important part of electricity supply systems, and this is something which we will be considering in this course. Again, as I mentioned, I should clarify here that we will not be doing a complete course on power electronics or a course on electrical power systems, but instead we shall actually consider a few concepts one by one, try to illustrate them with examples and also show you a few experiments. The last part of this course is regarding electrical grids, which will consist of high voltage bulk transmission, power electronics, HVDC and FACS, renewable systems which are actually coming into prominence now, and also control and monitoring. And importantly, we shall consider a few examples of how it is possible with today's communication and computing technology to actually do a kind of implement a wide area measurement system. So, these are the kind of things which we will be considering. These are usually some discrete topics which I think are important, and I hope after this course you will feel many of your concepts are reinforced. In this first lecture today, we will be considering in fact a theoretical aspect. Today's lecture will not have any experiments or examples, but the basic physics of the laws which govern the interaction of electrical charges. In fact, the equations are the well known Maxwell equations, and what we will do today is slightly revisit these equations and understand what they mean. So, what we will do next is go to the slides on Maxwell's equation and revisit these. So, when you go to when we try to understand the basic physics of our engineering discipline, the first thing which comes to mind is how charges interact with each other. Of course, the first point is of course what are charges? Well, charges are an attribute. It is impossible to describe them, describe what is a charge. It is a very fundamental concept, it is an attribute and it is found in nature, and there is no further explanation of that except that there is a certain quantity called a charge, and these charges interact between themselves, that is they exert forces on each other. And all of us know that in fact the first law which we learn of electromagnetism is in fact Coulomb's law. So, the Coulomb's law states that the force between two charges is equal to 1 by 4 pi epsilon naught q1 q2 by r12 square, and this force is of course a vector, and the important thing is which you should remember is that this force law is actually valid only under static conditions, that is where everything is all the charges are in fact steady, okay, everything is actually in steady state. Now remember that force is a vector and therefore we are using this arrow notation. Force, and what you see here in these equations is F12, that is the force on charge 1 because of charge 2 is equal to q1 q2 by r12, that is the distance between the charges, and E12 is of course a unit vector in the direction 1 2, that is an arrow pointing from which has got an arrowhead at charge 1 and starting from E2, that is the direction. So, E12 is a unit vector. So, what we have here is if you have got a charge at 1 and a charge at 2, this distance is r12 and this is charge q1 and this is charge q2, and the force is of course this E12 direction is this E12 bar, and of course the force is also in this direction. Of course, I must mention here is that here I have assumed that both charges are positive. There are in fact in nature positive and negative charges. In case you got a negative charge of course, for example, if q1 and q2 are of opposite charge, the forces are not repellent, but actually will try to attract in the attractive direction. That is if q1 is negative and q2 is positive, the force in fact will be not in this direction, but in the opposite direction. So, this is something which we learn in high school physics. Epsilon naught of course is the permittivity of free space, and that has got the unit farad per meter. Now, what is essentially the difference which we find when you try to generalize this law? I told you that this law is valid only during static conditions, that is in steady state where the charges do not move. A more general law is the Lorentz force law or the Lorentz force equation, which actually tells us that the force is equal to the charge and it depends on the electrical and magnetic fields at that point where the charge is. So, now instead of a direct action at a distance formula, you have a kind of indirect way of writing the forces, that is in case your electrical field at a given point is E and the magnetic field or rather the magnetic flux density at a point is B, both are vectors at a given point, and if you put a test charge q there, it will experience a force which is given by this equation. Now, the thing is that V here is actually the velocity of the electrical charge q. So, this depends not only on the charge, but also the velocity of the charge. So, this force in fact has got a velocity dependent term. So, if you have got a charge at a given point and it is moving, you will find in fact that it has got a force due to that if there is a magnetic field there as well. In fact, if you look at force law, you will find that this force law has a component V cross B, and this is of course the well known cross product of vectors. Just to revise what cross product is, if you have got a velocity v, a charge has got a velocity v, and there is a magnetic field at that point b bar, and then the force experienced by this charge which has got a velocity v is given by the cross product of v and b. And how do you take out the cross product? Well, the magnitude of v cross b is vb sin theta, and the direction is given by using the well known right hand convention, that is, you take your right hand and place your fingers at the first vector here, that is v, and then move towards b, and the force is actually then in the upward direction. This is called the right hand convention for the cross product. So, the force due to a moving charge in a magnetic field B is given by the cross product. In fact, in case your velocity is in this direction and the magnetic field is in this direction, and this is theta, the magnitude is again Vb sin theta, but the direction now is you place your fingers in the direction of the first vector v, move towards b, and therefore, the direction of the force is actually downwards. So, this is essentially how one has to use this rule. The Lorentz force equation is true in general, and therefore, it is applicable under both static as well as dynamic conditions, as we shall see a bit later. Now, remember here that we are using a kind of an indirect way to compute the forces. We are defining quantities called electrical field intensity, which has got the units of volt per meter, and the magnetic flux density, which has got the dimensions, or rather the units Tesla. Now, these are kind of intermediate quantities which we need to find out. In the earlier formula by Coulomb, you found that the forces was simply the product of the charges, was proportional to the product of the charges. But here we are talking of an intermediate quantity which has to be determined. Now, this means that you need to have a separate set of rules or laws which actually determine how E and B are determined. So, these laws are in fact called Maxwell's equations or Maxwell's laws, and we shall see these the set of laws in the next few slides. If you look at Maxwell's equations, they can be actually very interestingly, they are very neat set of equations, they are a very compact and precise set of equations. They are expressed in terms of vector calculus terminology, and what we see here are the 4 Maxwell's equations. In fact, they look very intimidating at first sight, but they are not that intimidating. In fact, they are quite simple to in fact state even in words. Now, what these Maxwell's equations in fact are is now described to you in the next few slides. For example, the first law is called the Gauss's law for electricity. Gauss's law of electricity states that E dot ds over a closed surface is equal to 1 by epsilon naught, the permittivity, into the charge enclosed by this closed surface. So, what you have is rho dV, in that rho is in fact the charge density and dV is the volume element. Now, so what does this mean? Let us look at this slide here. What does this mean? In fact, you will find that this is the symbol for a surface integral. So, the surface integral, what does it mean? You take a closed surface. In fact, this round circular symbol means it is a closed surface. So, take a closed surface. Here I have shown a sphere, but it is not necessary to have a sphere. You can in fact have any closed surface. It could be an ellipse or any slightly irregular shape, but it should be a closed surface. You take a closed surface, you find out what the vector E is at every point, or rather if E is obtained at a certain point on the sphere, I call this this point, and now I take this E and do a dot product with an elemental area vector. So, what we mean here is this ds is a small element on the surface. It has got the dimensions of area. So, this white patch which you see here is a small area on this surface, and this at the point at which the electrical field E is there, we draw a tangent plane at that point. We take a small elemental area at the point at which this tangent touches this surface, and what we do here is we assign a direction to this area, we call it an elemental area vector as the outward normal at that point. So, ds bar is in fact the ds bar which you see here is an elemental area which I am shown here, this elemental area, and it has got a direction of the outward normal. So, this is ds bar vector. So, at every point you can actually find this ds bar, it has got the direction which is given by the outward normal at that point. How do you get the outward normal? Well, draw a tangent which just touches that surface at that point and draw a normal to it. Outward normal means that in case you move in that direction of the outward normal, you will come out of that surface. So, that is what I mean by outward normal. You can also have an inward normal, but here we shall use the outward normal. So, you take the outward normal at that point and assign the elemental area that direction of the outward normal, then take the dot product of E and ds, that is E dot ds, and do this for every point on the sphere, and you sum it all up. Of course, since we are talking of elemental volumes, infinitesimal areas, and therefore it will be kind of an infinite summation. So, this effectively becomes an integration. So, this is what is meant. So, you at every point on the sphere you do E dot ds and then integrate it over the entire surface, and this is equal to 1 by epsilon naught into the total charge enclosed. In fact, this is a volume integral, the volume is whatever is enclosed by this surface, and rho dV, rho is the charge density in coulomb per meter cube, and therefore, this rho dV integral over this volume is actually the charge within this surface. So, what this says is, this law states is that the electrical field, you can in fact put in a certain way that the total flux of the electrical field through this surface is equal to the 1 by epsilon naught into the charge enclosed by the surface. So, this is what Gauss's law of electricity is. The next law is the Gauss's law of magnetism. In fact, it has to be actually computed in a similar way. You take any surface, this is shown as a sphere, but it could be any surface. Then what you do is you compute B dot ds. So, it actually means you have, if you have got a vector B at a certain point and you at that point draw a tangent plane to the surface, and you take an elemental area at that point and assign it the direction given by the normal, outward normal at that point, and take the dot product of it and then integrate this this quantity over the entire closed surface. So, as I mentioned earlier, this circular symbol here indicates a closed surface. So, you do this for a closed surface, and then what you see is actually this will turn out to be 0. So, this is the law of magnetism, and this another way of stating it is that the total electrical flux through a closed surface is 0. So, the total magnetic flux, thank you, is actually 0. Now, this also means that magnetic monopoles do not exist. So, you cannot have a source of magnetic field, you can say. So, you can't, if you have got, in fact, unlike in an electricity, when you talk of electrical charge where electrical field lines emanate from the charge, in fact, you can have a non-zero electrical flux through a surface if there is a charge inside it. Unlike that, magnetic field, you cannot have magnetic monopole. So, whatever enters the surface, the electrical the magnetic flux entering the surface will actually come out of it. So, that is an interesting law or observation in nature. The third law is what we are mostly familiar with. It is called Faraday's law. In Faraday's law, what we really, it is slightly more complicated than the earlier law. What it says is that if you take a closed curve in space, so I will just indicate to you the closed curve, and what you do is this has to be closed, so that that circular symbol on the integral is actually indicates a closed curve, and in case you have got a closed curve and at every point on the curve I draw a tangent, I also take an elemental length along the tangent, I will call that dl, and this direction which you take of the tangent is based on a anti-clockwise direction, that is the convention I will use. This is dl, an elemental length, we will assign it this direction which is equal to the same as the tangent direction. So, this an elemental length in the direction of the tangent at that point. Of course, this tangent can have direction in both ways, but what we will do is we will take the anti-clockwise convention. So, we will take it is a kind of consistent with the right hand rules which you are applying, the right hand convention which you have applied before. So, what we will do is take the tangent in the direction clockwise direction, and at this point suppose the electrical field is E bar, in fact it could be in other directions as well, I am just showing you a possibility, and you take the dot product of E dot dl and then you integrate this E dot dl over the entire curve. That is what you will evaluate on the left hand side, and what it turns out to be, that is what Faraday observed, was that this is equal to the total magnetic flux emanating out of a surface which is bounded by this closed curve. So, what it means is that this is a closed curve, this is a surface integral, B dot ds is to be evaluated in the same way as I mentioned earlier, but the important thing is that this is evaluated not over a closed surface, remember there is no circular sign here. This is not to be evaluated over a closed surface, but over a surface which is bounded by this curve. So, what you have here is, so if you take this curve, this is one of the surfaces which is bound by this curve, and what you do is you evaluate B dot ds, but not over a closed surface, it is only on this surface which is bounded by this curve. So, the thing is of course here one important point which you should note is that the direction of ds which is to be taken here is determined by using a right hand convention again. So, if you take this, suppose this is the outer boundary of this curve, and you take the you take the anti-clockwise direction here, and in that case ds is in the upward direction. So, the direction of ds is the upward direction in case you take an anti-clockwise direction for your curve. So, actually all these curves have to be, you have to define the direction. If you take an anti-clockwise curve, anti-clockwise direction for the curve, in that case ds is pointing upwards. So, what you have essentially is B dot ds, it is integrated over a area which is bounded by this curve, and if you evaluate that, the derivative of that with respect to time and take the negative sign of it, you will find that it is equal to E dot dl. Now, to put it in words, what it means is that in case there is a electrical flux and it is changing, okay, in a surface, on a surface, then that you will find electrical field, a circulation of an electrical field in the on the boundary of that surface. Remember here the surface is not a closed surface, it is a surface which is bounded by the closed curve. Okay. So, we have a closed curve and a surface bounded by the closed curve. So, in fact, one of the points which you may wonder is that I have talked of a curve which is bounded by rather a surface, a surface which is bounded by the closed curve. Now, is this the only surface you have? The answer is no. You can take any surface. So, for example, instead of taking this surface like this, we can take, for example, a kind of lower a curve which is on the side shown here. In fact, here this could be, suppose B is in this direction. Remember that you have to choose ds in the upward direction, because that is determined by the anti-clockwise direction given to this curve. Okay. So, if you define the direction of the curve to be anti-clockwise, then you have to take ds in the upward direction, not in the downward direction. So, again you do E dot ds and integrate it, you will find that it is equal to E dot dl. So, there is no unique way to define which surface, as long as it is a surface which is bounded by the curve. And the important point is, irrespective of which surface you choose, as long as it is bounded by this curve, if you evaluate B dot ds in the way I told you, this law of Faraday holds. Now, you may find it a bit surprising, but it is not, because actually, for example, if you have got one curve, you have taken a curve in the clockwise direction and you take the upper hemisphere as your curve, and somebody else chooses the lower hemisphere. Both of them evaluate, one of them evaluates B dot ds using the upper curve, and the other person evaluates B dot ds going into the lower curve. In fact, because of the earlier law which you have studied, that B dot ds over a closed curve surface is 0, the flux through a closed surface is 0. What it means is that if a person is computing the magnetic flux through this surface, it will also be equal to the magnetic flux emanating out of this surface. So, essentially both of whichever surface you choose, as long as it is bound by the same curve, you will get the same answer. So, remember that Faraday's law effectively states that you take any curve which is bounded by this curve, any surface which is bounded by this closed curve, as long as you compute this B dot ds appropriately, then you will get the same answer. So, the important point to be noted here is that the rate of change of magnetic flux on a computed over a surface is equal to the circulation of E dot dl on the curve which bounds it. So, that is essentially Faraday's law. The next law is in fact Ampere's law. In fact, Ampere's law states that in fact it relates in a similar fashion B dot dl. We had in fact considered E dot dl, the circulation of E dot dl over a closed surface. Now, we will consider B dot dl over a closed surface, the circulation of it. Mu naught here is called the permeability of free space, and Ampere, this law is called Ampere-Maxwell law because Maxwell introduced an extra term which was not, in fact, he introduced it and modified the law, and it turns out that this modification is required to make this law consistent with the conservation of electrical charge, which we shall see shortly. Now, what does this law state? It says that the circulation of B dot dl over a closed curve is equal to the total current flowing through the surface bounded by this closed curve. So, J dot ds, J here means the current density at every point. So, what you have here is the current density at every point, and this is essentially determined by this. So, what this means is J is the current density, this is in fact J dot ds evaluated over a surface is in fact the current flowing through the surface, what we call as current. Current is of course the number of charges flowing through a surface. in a given in a certain time. So, that is in fact the charge is flowing in 1 second over a given surface is in fact the current in amperes. So, the thing is that this was in fact Ampere's law was actually initially only stated this way, but Maxwell introduced this term because he found that if this term is not introduced, then the conservation of charge is violated. We will not derive this in this lecture, but let me just tell you that implicitly Ampere Maxwell law implies that the total current through a closed surface is equal to the rate of build up of charge within the surface, which makes a lot of sense. It is in fact the conservation of charge. What it says is that if you take over a closed surface j dot ds, it is not going to be equal to 0. Suppose this is the current density represented by lines, and you find out how much is being, you take a closed surface and you try to find out how much is entering this closed surface and how much is leaving it, and you will find that if there is a difference, if there is a net value to this j dot ds, which is the total current entering a closed surface, what you will find that it is equal to the amount of charge which is building up inside the surface. So, what it really means is that it is a restatement of the conservation of charge. You can't just have charge emanating or being created, it again has to come from somewhere. Okay. So, this is essentially the law of conservation of charge, and Ampere Maxwell law in fact is consistent with the law of conservation of charge. Now, we will go back to the Maxwell's equations. Let us just have a relook at them again. So, if you look at Maxwell's equations, these are written in terms of integrals, and although they are easy to state when you in terms of integrals, they are not very useful when you try to compute the electrical and magnetic field, especially when you have got a general situation. In some very specific instances where there are a lot of symmetries, etc., it is possible to in fact evaluate these integrals quite easily. But in most other situations, you need to come to a form of equations. The same equations you have to express in what is known as the point form or the differential form of the equations. So, what are this point form? They are equivalent ways of representing Maxwell's equations. In fact, let us just as an example, again in this course, as I mentioned, we will not be deriving every law or deriving every expression, but we will do it for one law, that is Faraday's law. So, we will express Faraday's law not like an integral equation over closed surfaces, etc., but in point form, as we shall see soon. So, if you look at Faraday's law applied to a very small closed curve. So, what we will do is we will start off with Faraday's law. What is Faraday's law? Faraday's law essentially is this. Now, what we will do is we will apply this Faraday's law to a very small, infinitesimally small closed surface. So, what we will do is let us just move on to a slide here. So, if you look at Faraday's law applied to a very small closed curve, I mean this closed curve is of infinitesimal dimensions. So, what you have here is a closed curve in the xy plane. So, let us for the timing, for simplicity, we will just try to look at a closed curve in the xy plane. Now, if you take this closed curve, there is a midpoint there at which the electrical field E and B are expressed as vectors, which are given at the top of the slide, and there are 4 points, 1, 2, 3 and 4, which are shown there. Okay. Now, the important thing is that we are going to apply Faraday's law, which we have already expressed in the integral form, and try to apply it to a case where you have got an infinitesimal infinitesimally small closed curve. Now, let us take for convenience a curve which is a rectangular curve with one side dx, having length dx, dx of course means it is infinitesimally small, and one side is dy, and if you look at the area of this area of one of the surfaces, we will just take the surface which is in the plane xy itself. We have a choice which surface to take, but we will simply take the surface which is in the plane xy itself. This rectangular surface which is in the plane of x and y, the area, the magnitude of this area is dx into dy as given below, and since we will be actually using a counterclockwise, anti-clockwise direction for this curve, we will assign an anti-clockwise direction to this curve. The ds bar, the vector ds bar will be in fact dx into dy into az which is coming out of the page. Now, so b dot ds, if you take the dot product of b at the point, we will assume that this curve is very small. So, b is almost the same everywhere in this curve. So, b dot ds is the dot product of b and ds, and if you take the dot product, because this ds has only the component in the az direction, b dot ds will be in fact bz into dx dy, because the dot product between ax and az is 0 and the dot product between ay and az is also 0. So, the only term which remains is bz into dx into dy, and as you know, a dot product will yield a scalar quantity. So, bz into dx dy is in fact a scalar quantity. Now, we will go to the next slide. What we will see is that the same curve, I slightly blown it up, the elemental lengths dl for each side of this curve are shown here. So, for point 1 or the side 1, the dl1, I will denote it as dl1, is nothing but minus dy into ay, okay, minus ay, because this at this point the curve is actually pointing in a downward direction. Similarly, dl2 is dy into ay and dl3 is minus dx into ax and dl4 is dx into ax. So, these are the elemental lengths, length vectors on all the 4 sides of the same curve, which we have discussed some time back. So, what you have here now is, if I want to take out E dot dl over the first side, we will assume that this is an elemental length dl, and so if you do it on the first side, you will find that you get E1 bar, E1 dot minus dy into ay. If you go to the previous slide, let us just go there. On side 1, let us say the electrical field here is E1. So, E1 dot dl will turn out to be E1 dot minus dy into ay, and in fact E1 is, suppose I define in one previous slide I defined E at the midpoint of the curve. So, E I defined here as what we have seen in the first expression here, E is equal to this, and therefore, if you go to side 1 here, E will be slightly different from what it is at the midpoint. So, but since this distance is very small between the midpoint and the side 1, we have taken an elemental curve, what we find is we can express E1 is nothing but E1 bar in fact has components in the x, y and z direction, but if we take a dot product between E1 and minus dy ay, only the y component of E1 will come in the expression. The y component of E1 is nothing but Ey minus the derivative of Ey, partial derivative of Ey with respect to dx into dx by 2. Why is that so? Because if you look at this distance between the midpoint and side 1, it is dx by 2, and we assume that this distance is very small. So, it is like a Taylor series expression for the y component of E1. So, the y component of E1 is Ey minus dEy by dx into dx by 2. Now, so this component is the only one which remains, because the dot product is between E1 bar, which has got x, y and z components, but dl1 has only the y component. So, when you take out the dot product of this E1 and dl1, what you get is this. In a similar fashion, you get for side 2 and side 3 and side 4. So, can you just show the expressions? Yeah, side 1, side 2, side 3 and side 4. And if you actually sum them all up, so what you do is you sum up all of these. Since this is an infinitesimally small curve, what you find is that you will get in fact the expression on the right hand side. So, if you sum this up, you will get this expression. Therefore, E dot dl for this extremely small curve on the xy plane is actually given by this, and as per Faraday's law, this is equal to B dot ds, which we already took out in the the initial slide. So, what you get is this expression, and this also means, if you come to the next slide, the last, so I have just cancelled dx dy from this from the previous, if you just go to the previous expression. So, on both sides you cancel dx dy, and what you get effectively is the last expression here. Now, you could do this for a curve on in the yz plane as well as in the xz plane and get these 3 sets of equations. So, Faraday's law implies these 3 sets of equations. These are scalar equations, but you can express them as vectors as well. So, what we really obtain, you can in fact show that if you compute the expression nabla cross E bar, this in fact is called del, in fact not nabla, the Greek symbol is nabla, but this is called del cross E, or in other words the curl of E. The curl of E comes out to be minus of dB by dt. So, how did we get this? In fact, we found out by applying Faraday's law, if you come to the previous slide, that these 3 expressions hold. The first expression you multiply by the unit vector Ax, the second expression on both sides multiply by Ay, and the third expression by Az, and you will find in fact that this curl operation or the cross product operation between del and E, where del is defined is a kind of an operator which is defined in this fashion, it is a vector operator, and if you in fact compute the cross product of this operator with E, you will get exactly the equations which we have got in the previous slide. And in compact notation, what we have is Faraday's law implies that the curl of E is equal to minus dB by dt. Now, this is a kind of a differential kind of form of a point form of the equations. This is very useful when you are going to do any kind of computation of electromagnetic fields. But I hope I have slightly demystified what seems to be a very complicated concept called a curl, and you can show that it is the law which we get in the point form is an equivalent to the integral law. So, this is essentially Faraday's law in point form. In fact, you can show that you can obtain similar laws for the Gauss's law of electricity, similar point form of Gauss's law of electricity. So, it turns out that Gauss's law of electricity in the line integral form is nothing but in the point form is nothing but the divergence of E is equal to rho by epsilon. Rho is the charge density, epsilon naught is the permittivity, and therefore, what we have is essentially a neater and a differential expression for Gauss's law of electricity. Now, importantly, I have not derived this, but let me tell you a way, indicate to you how you can derive it. You try to apply this integral form of Gauss's law to a elemental or infinitesimally small volume, and you will be able to derive this quite easily. Remember that the divergence of E is equal to is divergence of, this is called the divergence of E, it is the dot product of the del operator which I have just mentioned some time back with E bar. Now, so actually, as I mentioned some time back, the divergence of a vector is in fact a scalar quantity. By mistake there is of course a term Az, this is actually is wrong, there should not be an Az there. It is in fact del of E is in fact quite a simple expression which you get here, which I have shown here. So, let us go back now just to summarize to the next slide. These are Maxwell's equations in the integral form, and what we have in the next slide is in fact Maxwell's equations in the point form, and this is something which you are familiar with and possibly done in a high school or first year science or engineering physics course, but I thought it will be useful for you to revise this again. Now, if you look at these laws and try to apply them to real life materials, one of the important thing when you apply this law to real life materials is that real life materials themselves are consisting of charges. In free space, that is vacuum, there are no charges, and rather the vacuum itself does not have any charges, we call it free space. But if you look at a material in fact contains charges. It may be, most materials normally are electrically neutral because the number of positive and negative charges balances out, but they do contain charges in atoms and the nuclei of atoms as well as the electrons. Now, so when you are trying to apply Maxwell's law is true in general, but when you are trying to apply them to a material, you will have to consider each and every charge in that material, and also if those charges are moving, like due to the spin of the electrons or the movement of the electrons and nuclei, in that case you will need to consider the current densities due to that as well. So, that becomes a bit tricky because this is difficult to account for. There are so many atoms and electrons, atoms and charged bodies within a material that it becomes difficult to in fact account for all of them. So, from a macroscopic point of view, what we do is, we do not actually consider or apply Maxwell's equation by looking at the effect of each and every charge in a material individually. Suppose I have got a material, I will only first consider the external charges. So, what I will do is I will consider only the external charges, not the ones which are there intrinsically in the material themselves, and let rho be the external charges. Now, if you want to apply Maxwell's equations, what you do is consider only the external charges. Remember that if there is external charges causing an electrical field within a material, what will happen? The charges within the material will move because they experience forces due to the electrical field caused by the external charges. Now, because they move, the negative charges will move in the direction of the positive external charges, and the positive charges within the material will try to move towards away from the positive charges. So, just to illustrate this, suppose I have got a plate, metallic plate, this is the, and which has got charges. Now, if somebody asks you if these are the charges present in free space, compute the electrical field, you can apply Maxwell's equations and compute the electrical field at various points in free space. But suppose instead I put a material inside which has got atoms which in turn have got charges, although the material overall is electrically neutral, it has got positive and negative charges. What will happen is that the electrical charges in the atom, the negative charges will get pulled towards the positive charge, and and the positive charge get pulled towards the negative charge. So, the electrical material gets polarized. Because of this polarization, the effective electrical field inside gets altered than what it would have been if there were no charges in the material at all. Because of this polarization, the electrical field in fact decreases. In fact, the amount of electrical field is lesser than what it would have been if free space were present, rather if there was free space, there is nothing present. So, the material within actually alters the electrical field, and a rough way of taking into account this is to remember that the electrical field slightly decreases because of this polarization, because if you look at it, you have got the negative charges have moved slightly upwards and the positive charges have gone down. So, it kind of to some little bit of an extent cancels this effect of the external charges. So, if you are considering only the external charges and you try to get the electrical field in free space, and you obtain the electrical field using the formula which in point form, in this fashion you apply this law and try to compute the electrical field in free space, and now you put this new material. Now, if you put this material inside, you will find the electrical field has actually reduced. So, what you will find is this electrical field will be equal to P external by rho external by epsilon naught, but then what you do effectively is multiply by the scaling factor. What this does, this scaling factor epsilon r is also called a relative permittivity. It is a kind of factor which accounts for the fact that now the electrical field is slightly lesser in the material because of the polarized charges within the material. So, this is epsilon naught r is equal to epsilon. So, all what is done in Maxwell's equations is consider only the external charges, and but then put a correction factor, or you multiply a factor epsilon naught r with epsilon naught, and in fact this polarization increases with increasing electric field. So, this is a kind of a proportional correction which you apply. So, that works out quite well. So, this of course is the electrical field within the material. Of course, we are is the electrical field uniform? We are not saying that the electrical field is uniform. All we are saying is that the gross effect, or the you can say the coarsely, if you see, electrical field is slightly lesser if you introduce a material which gets polarized. Now, a similar concept can be applied even to the magnetic field. If you have got a magnetic field due to a current, suppose you have got an external current, there is a current flow J dot ds. So, what you have really is, because of this current you will have some magnetic field. Remember, this is the law. So, if you have got a current, you will have a magnetic field. Let us assume for the time being that this is 0. So, what you will have is a magnetic field, but in case I put a material because of which the material, suppose I put a material which internally has got circulating currents. In fact, materials in fact have got charges in their atoms and nuclei, and these charges usually have are moving and they have got what is known as a spin, and this effectively causes them to behave themselves like magnets or currents. So, in fact, a material has got atoms and these atoms have got internal currents, you can put it this way. Now, again to take out the magnetic field, overall magnetic field, you will have to take into account all these currents, atomic currents, strictly speaking, if you want to apply Maxwell's law the way I have shown it here. But one of the interesting things which happens is that if you have an external current, which is current density at a point is given by J bar, then the magnetic field which it causes in free space, you will get a certain value at every point, but the same thing free space is replaced by some material which has got atomic currents. Usually if you have got a material in which these atomic currents cause a magnetic field, and when you place this material in a magnetic field, all these currents kind of get aligned to this external current in some way, then the magnetic field inside gets enhanced. Now, if you have got a material of this kind, then you will find that the magnetic flux density B may become quite large. In fact, these materials are called ferromagnetic materials. In ferromagnetic materials, you can say the atomic magnets all get aligned with the external magnetic field causing external current. So, what we do is that for example, in a ferromagnetic material, you will find that for the same J, you will find a larger field, magnetic flux density, and therefore, you can, if you multiply both sides by mu naught plus epsilon naught mu naught, you will find that you can, and if you only consider the external currents, then to account for the magnetic currents, all you have to do is multiply it by the relative permeability. In some materials, mu r can be quite large, and because of all the atomic magnets all align with the field caused by the external current, and as a result of which you will have a very large field. In fact, mu r is quite large in ferromagnetic materials, it can be order of thousands. So, mu is equal to mu naught mu r. This mu r is a kind of a rough or coarse way to take into account the effect of these atomic currents. Okay. So, when you are actually computing your magnetic field, you will only consider the external currents. The effect of the atomic currents is actually approximately handled by multiplying mu naught by a factor mu r. Now, remember this, I am assuming that this can be handled in this way. Actually, I have just multiplied mu naught with mu r and we hope that it works, but it turns out that for many ferromagnetic materials, this mu r is not constant, it is dependent on the external currents, in the sense that mu r is not a constant. So, it depends in fact on the B which is there. So, this aspect, this is a nonlinearity in fact. So, this mu r is not a constant, it depends on the field itself. So, this is called saturation or nonlinear behavior of a ferromagnetic material. So, this is how we approximately handle the cases in which you do not have free space, but instead have a material present. So, what we have here now is the Maxwell's equation. Only thing is that we replaced epsilon with mu sorry, this is Maxwell's equation for free space. If you try to go to Maxwell's equations inside materials, you have replaced epsilon with epsilon, epsilon naught with epsilon as mentioned before, and mu naught with mu, and mu is equal to mu naught mu r. So, that is the change we need to apply. Yeah. An interesting thing happens when you consider only static conditions. Static conditions means all the derivatives are set to 0 in the Maxwell's equations. If you do that, what you will have is E dot dl, for example, over a closed curve, integrated over a closed curve, will come out to be 0 because dB by dt becomes equal to 0. Similarly, Ampere-Maxwell law, you will find that the term corresponding to dE by dt is missing, the last equation. So, you just have these two. In fact, since the total electrical current entering a surface, if you take a closed surface and you look at the current entering and going out, if there is a net, if the current going in is more than the current going out, you will have a buildup of charge. So, charge will go on increasing. So, that in a static scenario cannot happen. So, one of the important things in a static situation is that the charge is also constant in space. Okay. So, it also means that the the flux of the current is equal to 0, there is no charge build up anywhere. So, this is Maxwell's equations under static conditions. In fact, we saw some time back that Coulomb's law holds in fact only for static conditions, it does not hold true, is not true in general. In fact, what we see here is that this is something we will not derive, but just to make a correlation with what we have done in possibly in high school physics or in the first year of an engineering or science curriculum. In fact, if you use Maxwell's equations under static conditions, they are nice formulae in fact which try to directly give you using action at a distance kind of formulae what B and E are. So, for example, the first equation is Biot-Savart's law, and what it says is that the magnetic flux density at point 1 due to a current density at point 2 is given by this formula mu naught by 4 pi, and you integrate over the area in which current exists. So, you will integrate J dot J cross E12, again E12 is the vector which you have defined before, is the unit vector with the arrowhead at point 1. So, E12 is in fact defined as something, I will just go to slides just to make sure that. So, B at point 1 due to a current at point 2 is actually this E12 vector is in this direction, it is a unit vector. Okay. So, E12 bar is in this direction. So, this is what I meant by E12. So, all you have to do is, if you have got a current density at this point in this direction and E12 is in this direction, what you need to do is the cross product of E into J into, so if J is the local current density at this point, then the cross product of J into E12, J cross E12 has to be used in that Biot-Savart's law, and therefore, you will in fact get the formula which is given there. Okay. So, this is essentially the law of Biot-Savart, and similarly E can be obtained. E is equal to 1 by 4 pi epsilon naught into the charge density integrated over the place where the charge exists, and in fact this if you have got a point charge at the point 2, then this integral is nothing but equal to Q2 divided by R12 square. So, Q2 divided by R12 square into E12 bar. So, in fact, if you have got a point charge, this volume integral just will be equal to the charge at that point. So, if you go to the next slide, you will see that if you assume that V cross B is 0, then and we apply Lorentz force law, which is true in general, you will find that the force which you will get due to 2 point charges, remember that E1 now will be equal to 1 by 4 pi epsilon naught into Q1 into E12 bar, where Q2, where Q2 is the point charge at location 2. So, if you want to apply this to point charges, you will find that you will get Coulomb's law. So, Coulomb's law is essentially the application of Maxwell's equations to Maxwell's equation and Lorentz force law to static under static conditions. Remember that this formula E1 which is given here is valid only under static conditions. So, under static conditions you can get B and E directly from the current and charge densities using a action at a distance kind of formula. Now, one more interesting thing about static conditions is that you can express electrical field as a gradient of a scalar potential. So, you can define under static conditions, let me re-emphasize that the electrical potential which is defined by 1 by 4 pi epsilon naught and the volume integral which is given there. The volume integral is actually evaluated in the region where the charge exists, and this potential, if you take the gradient of it and multiply it by a negative sign, then you will get the electrical field. So, this in fact the fact that you can express electrical field as the gradient of an scalar quantity is possible only because the curl of E is equal to 0. So, this is a interesting aspect of vector calculus, that if some curl of a vector is 0, it can be expressed as the gradient of an electrical potential. Gradient is simply the product of the del operator into phi, so acting on phi. So, in fact, if you have got phi, then gradient of phi is nothing but d by dx. Remember, this is equal to if you actually compute gradient of phi, that comes out to be so electrical field can be expressed as negative of gradient of phi, and phi here, remember, we have to be careful about notation. Phi here is actually the electrical potential at a point. Now, some more interesting aspects which come from all this is that if we evaluate the integral, line integral from a to b, E dot dl, from point B to A, you will find that the answer which you will get is simply called, it will come out to be difference of the potentials evaluated at A and B, and it will not depend on the path which you follow to get this, when you evaluate this integral. So, that is an interesting thing which occurs in under static conditions, is that the electrical field can be represented as the electrical field integral E dot dl from A to B is not path dependent. So, that is an important aspect which you should remember. So, if I just try to explain this again. So, what you have got is this integration E dot dl from A to B, it does not depend on the path which you follow. So, remember that E dot dl, what do you mean by E dot dl? You take a curve, dl is of course an elemental length with direction, let us say we take the anticlockwise convention this way for a curve, and you move from B to A, then you can move in B to A in this way, or you can even move in this way. So, you can move like this or like this, but it turns out that if you take out this integral from B to A, if you take it out using this path or this path, you will get the same answer. That is, under static conditions, the path does not matter when you compute the this E dot dl between points in A and B. This is not surprising, because in a closed loop, under static conditions, if you write the integral form of Faraday's law, it turns out to be 0 for a closed surface. So, it also means that if you go along this path and come back along this path, the answer will be 0 for a closed curve. So, if you take not a closed curve, but integrate only from B to A, the path will not matter, because A to B, when B to A, when you integrate E dot dl is going to be the negative of what you will get when you integrate from A to B along this point. So, what it means is that this B to A along this path and B to A along this path, when this is evaluated, will give you the same answer. So, also it means that this integral B to A of E dot dl does not depend on the path, and in fact it is equal to the difference of the potential at point A and point B. So, in fact, we also come to this concept of a potential difference. So, potential difference is something with under static conditions we can define potential, and the difference in potential does not depend on the path by which you compute E dot dl. So, that is an important thing. Another interesting point under static conditions is that if you have got a finite isolated conductor, and then in steady state the electrical field inside the conductor is 0. Remember, what is a conductor? Conductor is a material which has got a lot of free charges which are free to move. Now, in steady state, the electrical field inside the conductor has to be 0, because if electrical field is not 0, the charges within the conductor will feel a force and the charges will move. So, it contradicts the fact that you are in steady state. So, if you are in steady state and charges are not moving, you will find in fact that the electrical field within the conductor is 0. So, there is no charge accumulation. So, if you have got a conductor and there is no charge accumulation, that is, things have reached steady state, there is no further continuing accumulation of charge or movement of charge, it also means that the electrical field within the conductor is 0. So, an isolated conductor in which there is no continual movement or buildup of charge, you will find that the electrical field inside is 0. So, in static conditions for a finite dimensional conductor, you will find in fact the electrical field inside it is 0. And of course, this does not apply to a situation where you have got a conductor and somehow you are pumping in charges from one end and withdrawing exactly the same amount of charges at the other end. In that case, there is no buildup of charge within the conductor, but it is possible under this circumstance to have an electrical field within the conductor because of the resistance of the material. You may have a situation, we shall see later when we consider a resistor, that you can have a situation where you can have an electrical field within the conductor if under steady state conditions as well, but there is no charge buildup because whatever is going in is coming out. So, but in case you have got an isolated conductor in which there is no external source of charge or no external extraction of charge, then in that conductor the electrical current in steady state will be 0. So, an isolated conductor will certainly have electrical field equal to 0 in steady state. A non-isolated conductor can have an electrical field within a conductor, we will see that later when we consider resistance. If there is a source of charge which is pumping in charges here, and removing exactly the same charges here. Okay. So, then there is no charge build up, you have got a steady state current, and yet you can have an electrical field within the conductor. So, not having electrical field within a conductor applies to the case where the conductor is isolated and we have reached steady state. Okay. So, under these circumstances in fact this conductor has no electrical field, but the potential also such a conductor is also an equipotential, because if E is equal to 0, then it also means the gradient of V is equal to 0. So, it also means that this conductor which you have is at the potential is a constant. So, we call it an equipotential. So, under steady state conditions isolated conductor is in fact an equipotential surface. Now, the last part of this lecture is in fact the origin of Kirchhoff's laws. Now, we will revisit this again in our next lecture, but I will just give you a kind of a curtain raiser in this lecture. There are two laws which you have learned. Del cross E is equal to minus dB by dt, this is Faraday's law, or equivalently in the line integral form, this is what is Faraday's law. And there is another law which is implicit, which comes from the Ampere-Maxwell law, is the law of conservation of charge. That is, if there is a net flux, if the flux of current through a closed surface is non-zero, there has to be a build-up of charge in that surface. So, these are two laws which actually lead us to Kirchhoff's laws, Kirchhoff rules. So, this is something which we will discuss a bit more in detail in the next lecture. This just to kind of give you a kind of curtain raiser to what is coming next. In the next lecture, we shall actually have a bit of experimentation and look at real life devices like inductors, capacitors, resistors, the Kirchhoff voltage rules, how they actually come from the original Maxwell's equations is something we will consider in the next lecture.